Hello there. Let's do some application services that you need to know about for the CompTIA Network Plus exam. Now, if you're new to the channel, remember to subscribe and hit the notification bell. Otherwise though, let's get into it. So first of all, let's look at application protocol encryption and time synchronization protocols. And for the encryption, we're going to talk about TLS. Now, the reason why we're going to talk about TLS here and in the security videos for Network Plus is because a lot of our application services do get an encrypted counterpart. For instance, you get HTTP and HTTPS, and TLS is used to do that encryption. Now, if you are under the belief that no, it's actually SSL, well, TLS was developed as SSL's successor and took over from it quite a while ago. And in a lot of cases, people still refer to something as encrypted by SSL when actually it's TLS. It's a little bit of a manipulation to get the world to accept the newer, better encryption standard. Now, it operates between the application layer of the OSI model, layer 7, and the transport layer, or OSI layer 4. And it will be added to any TCP/IP application service that lacks encryption. Like I said, HTTP becoming HTTPS, FTP and FTPS, POP3, POP3S, and so forth. And what it does is it uses asymmetric encryption and digital certificates to apply the security. Now, we are going to do more about this in that latter network security video, but the short version of asymmetric encryption is we have two cryptographic keys. One key will be used to encrypt the data, and the other key will be used to decrypt. And then the digital certificates are used as a form of validation and authentication that you are talking to the genuine node and not some imposter. Now, TLS will provide us with authentication via the certificates, encryption via the keys, and integrity checking via digital signatures. Now, digital signatures are used just to prove that the message I sent is what you received and somebody hasn't tampered with it somehow. Now, the encryption does help a bit with that, but if we have an on-path attacker, or formerly known as man in the middle, the attacker could potentially be pretending to be the other party when talking to you, and pretending to be you while talking to the other party. But I do go into a greater discussion about digital signatures in my Security Plus series. Now, TLS 1.3 is the latest and recommended version for use both in the CompTIA N10-009 syllabus for Network Plus and the SY07014 for Security Plus. You can still get away with using TLS 1.2, but it is not considered as secure as TLS 1.3. Now let's talk about time with NTP, or the Network Time Protocol. It has one of the easiest to remember port numbers, 123, and it uses UDP for transport services. And NTP offers us network time synchronization, where we can go and check what the time is with a network server, and it can do this down to a millisecond level of precision. Now, what normally ends up happening is there'll be a couple servers all over the world. We'll have a look at the infrastructure now. And what they do is they host the current UTC time. And then the clients will adjust that with their locally configured time zone. The problem with anything that measures time is time drift can occur. No clock system, whether it be analog or digital, computer or otherwise, is going to be perfect. Time will shift for a variety of reasons. So to account for time drift occurring, there are two methods that we can use. The first one is called the slew method, where if the time drifts by a few seconds, NTP will correct it by a few milliseconds, check the results, and do it again. And check the results until it's brought it back to the correct current time. The problem though with slew method is it takes a bit of time to do. So when time drift occurs that is greater than a few seconds, NTP will do a hard reset with what's called the slam method. Now let's look at NTP's infrastructure quickly. So the way NTP works is we have an atomic clock, referred to as an NTP Stratum 0 appliance. Stratum 0 just means that this is the source of the time. And we usually use an atomic clock that measures the rate of radioactive decay of a particular isotope. Now, obviously this is not going to be TCP/IP accessible. So usually what happens is the institutes that run the atomic clocks usually have a server linked up to it called a Stratum 1 NTP provider server. And this server will be reading the time from the atomic clock and digitizing it and making it available via the network time protocol. The problem though with a Stratum 1 server is usually it's got very, very accurate time, but it's not normally very good at handling large volumes of requests. So usually what happens is the organizations that run these servers will work with Stratum 2 providers, usually service providers or big tech companies who have got the capacity to handle a large volume of requests. And that is normally the entity that we, the clients at Stratum 3, will engage with. Now that is if you are going to use a public NTP server. If you want, you could deploy your own private NTP server in your network and it gets the time from Stratum 2. And then with your own private NTP server as Stratum 3, your clients become Stratum 4 or greater. The reason for having your own local one is because of latency. If you go to a Stratum 2 provider over the internet connectivity latency needs to be accounted for. Whereas when your private NTP server just gets its time correctly, and then all your clients go to your local server, it is your network. Your network performance is a lot more guaranteed, predictable, and to a point, consistent. Nonetheless though, that is NTP's infrastructure. But we have another time protocol now that we could look at using, PTP, or Precision Time Protocol. Now this one also uses UDP, but it's got 2 port numbers. 319 for anything that is supercritical with accurate time, and 320 for general messaging. And unlike NTP, PTP does a nanosecond level of time precision, and is often used in environments where time is critical to be accurate, precise, and that accuracy and precision being down to a nanosecond level. You'll see this in situations like industrial environments, 5G telecoms, stock exchanges, and a whole load more. And it's got a very interesting feature. It can operate at layer 2 and work with hardware clocks. So it's a nice, interesting alternative to NTP. Now, in general though, most organizations will be fine with NTPs, time, precision, and accuracy. But in special situations where NTP is not accurate enough because of the millisecond level precision, PTP might be more suitable. Now, the way PTP infrastructure looks is it's a little bit like this. You get a server offering up the time called the Grand Master Clock. And then whoever gets the time from that could be a boundary clock. Now, the boundary clock is more likely to be a public-facing, client-facing server, whereas the grandfather clock is very similar to the Stratum 1 server of NTP. And the grandmaster clock with this boundary clock are in a master-slave relationship. I find it kind of creepy how often the master-slave relationship gets used in networking. Makes me worry a little bit about the people who define these standards. Anyway, now an ordinary clock device can connect to a boundary clock and receive the time from it. The ordinary clock treats the boundary clock as the master and it is the slave in that relationship. Or you could have a boundary clock feeding time to another boundary clock. Again, higher up the hierarchy you are, more likely you're going to be the master for that relationship and the slave if you're further down. And then you can have your ordinary clock down here, master slave again. Fantastic. Now let's look at web, file, print, and database services. HTTP, or the Hypertext Transfer Protocol. Probably one of the most well-known protocol services and applications that exist on networking nowadays due to the way the internet is currently used. Now, HTTP runs through TCP on port 80. And its job is to transmit the HTML source code and any additional resources from the web server to the client. Now, those additional resources can be pictures, video, fonts, basically anything that can't be expressed using pure HTML code. And what happens is the client's browser will take that code and render the website into a viewable form. This is why no matter how fast your internet connection is, there is always a momentary delay before the website appears because your browser has to render it real time, almost like compiling an application as soon as you want to run it. Now, the interesting thing about HTTP is it's also a stateless protocol. In other words, the way it was designed originally, a continuous session is not possible. So the fact that you can log in to something like Facebook or Instagram or TikTok and have an account and data that follows you, or do online shopping, and you can add stuff to your cart, move to another product, rinse and repeat until you're done, and then go out and check out with your credit card or debit card. All of that would not be possible without cookies. Cookies were created to be able to carry data from the previous page to the next one. Originally, you were meant to connect to a web server, download the HTML code, done. If you clicked a hyperlink, that was a new request and a new session, basically. But nothing that you did in the previous session or exchange would follow you through to the next one until cookies were created. What would happen is if you did anything on the first page, that would get saved in a cookie. When you went to the second page on a web server, and if that second page wanted something from the first page, it would ask you for that first page's cookie, where that data was kept, and then you'd provide it. That is how we managed to get these sessions, and it was the big thing that brought along Web 2.0. The only thing that's annoying about cookies is now they get used for a variety of different things, like targeted advertising, security, and stuff like that, which is beyond their original scope. Now, in deploying a web server, you get a couple of interesting options. You can run a dedicated server where you have a physical server with some sort of web hosting service like Microsoft's IIS, Apache, Nginx, XMPP, etc. installed and hosting a website. Now, this is your conventional deployment for a web server, and it can either be hosted by the organization who wants this website or an ISP, but it'll be a dedicated physical server if it's hosted by the ISP as a dedicated server. You can also have a virtual private server where the ISP hosts your web server as a VM, or you could go cloud hosting, where it runs in a cloud service provider's data center, and this option is becoming more popular as it's a lot more scalable and a lot more reliable than relying on your ISP. Think about it this way. Your ISP provides internet connectivity. That is their primary function. Anything else they do above that is nice, it's cool, it's wonderful, but it is a bit outside the scope of being a service provider. Now, obviously, in the modern day, we need to worry about security, and that's where HTTPS comes in. It is a secured variant of HTTP, and you're going to start seeing this now, but any encrypted variant of a protocol usually gets a new port number. In this case with HTTPS, it runs on TCP port 443, and it is using TLS, sometimes mislabeled as SSL. And the browser will usually indicate when you're using it via https:// in the URL bar, or if it doesn't show that, it'll do a padlock icon, maybe with some green coloring. And we use TLS and certificates to govern the site's trusted capabilities and the type of encryption it supports. Now, what's quite nice about these certificates governing the site's capabilities is, for instance, the certificate can validate whether the website is allowed to do transaction processing for something like an online store, which is pretty awesome. Or it could do something like telling you, hey, this site is allowed to host files that you can download. Speaking of files that you can download, let's talk about the original file sharing protocol, FTP, or the File Transfer Protocol. Now, FTP runs with TCP and it has two port numbers. It uses port 21 for control. So whenever you're connecting to and communicating with an FTP server, you're using 21 to issue instructions to it. And then you will either use port 20 to upload and download files if you're running FTP in active mode, or it'll use a random port number for the data upload and download if you're running FTP in what's called passive mode. Now, it is actually the original protocol of the internet, predating HTTP's use on it. Originally, the way the internet was working was you'd use FTP to connect to somebody's computer, browse their files, upload and download, and then if you wanted to look at the files, you'd look at it on your own local machine. That's pretty cool. Now, it is an old protocol, so as far as security goes, it does support authentication of the client, requiring that the user or the client do a username and password or something similar to that to prove their identity. But it doesn't really do much for encryption on its own. Now, Besides that, another interesting thing about FTP is that the client must have IP configuration on them. They must have an IP address, and they must either have a routing capability or a default gateway they can rely upon for routing capabilities. But as I said, it is a clear text transmission, meaning no encryption. But we do have secure variants, thankfully. And it is still considered slow by modern standards, but is used today because it is a very reliable protocol and can sometimes work in situations where newer, faster, better file sharing protocols don't work out so well for us. Now, due to FTP's age and popularity, some variants have spun off, like TFTP, or the Trivial File Transfer Protocol, which runs through UDP port 69. Nice. And it is kind of weird in how it works. It only supports upload and download of a file, or put and get, as FTP calls it. No directory navigation or file management can be done. So I can't browse what's on the server. I have to know what's there if I'm going to do a download operation. And I can't decide where the upload goes. It just goes into the default TFTP directory or folder. And with TFTP, it does not support authentication or encryption at all. We can't even add encryption to it. And the interesting thing about it, though, is the client doesn't need to have any IP configuration whatsoever. It is UDP based, and if needs be, it'll broadcast the traffic if IP settings are not present. But we generally discourage its use, except for some specific circumstances where TFTP might be okay. So for instance, maybe I will run a TFTP service on a router at a branch office and use that as a way to back up my config files and maybe even my device's OSs if they are text-based. But I'll make sure that that router is not internet accessible due to TFTP's inherent security weaknesses. Thankfully though, we do have secure variants of FTP. So you've got your original FTP protocol, and then there's actually two secure variants of it. You've got FTPS, where the S is at the end. Now when the S is at the end, it normally indicates that we are using TLS encryption. In the old days we used to use SSL encryption, but now it's TLS. And this means it'll be certificate driven and very popular for the internet because the certificates make it very easy for client and server to set up a secure encrypted session. And FTPS runs through TCP port 990. But there's another one that exists as well, called SFTP. And when the S for a secure variant is at the beginning, it usually indicates that we're using SSH encryption, which is key driven and uses SSH's port number 22. Anytime we use SSH to encrypt another protocol, it always ends up being remapped to port 22. But this is not ideal for the internet because it requires both the client and the server to remap a protocol to use SSH for security, which isn't too bad for an IT administrator to do on a server, but for an end user who might not have had this set up for them, that's a problem. That's why we prefer the certificate options where the client can just be running with a modern browser, a modern operating system, and the appropriate cipher suite, and they can get given the certificates and drive their encryption from there. That allows for an easy to set up encrypted service. I mean, think about it. Anytime the average home user connects to an HTTPS site where the S is at the end, they don't have to do anything special to have that encrypted connection. At most, they have to just log into that site with their profile. But otherwise, it works pretty well. Now, for newer protocols, a very popular one is SMB, or Server Message Block. It runs on a couple ports, using port 139 with TCP. If it's running in an older environment that still uses NetBIOS. In more modern networks, it's usually running on port 445. Again, also using TCP for transport. From a support perspective, it runs in Windows natively, and in Linux, you can use it if you have Samba installed. And considering that you've got two options now for file sharing between Windows and Linux, you can use Samba on Linux to make it work with SMB shares, or you could use NFS, Unix and Linux's file sharing service, on Windows to make Windows work with Unix and Linux share servers. We generally advise do the SMB option. It is considered better in terms of security. And the current version that you should be looking at using is SMB version 3, which supports message encryption natively. It has its own internal encryption, no need to add TLS or anything like that to make it safe and secure. SMB version 2 and below are okay to use, but please appreciate the lack of security options and validation of the parties you're communicating with. Now, another interesting way to approach file storage in modern networking is to use network attached storage, or a NAS device. Now, with network attached storage, what we have is a network appliance that is dedicated to providing file level share access to the network. Now, when we say file level, what this means is you can see the files, even the folders or directories that they're being held in, but you do not see the actual physical disk. You don't have what we call block level access, where you can see sector by sector what's on a drive. Now, most NAS appliances are Linux-based operating systems that are bespoke or specific to that NAS appliance. Thankfully, though, being Linux, it's customizable and will support a multitude of file sharing protocols and services, such as FTP or FTPS, SMB, and many more that are outside the scope of Network Plus at the moment. The only thing you need to bear in mind, though, with NAS appliances is they share the same network bandwidth with other appliances and services. So if you have a huge amount of web traffic, print traffic, voice over IP, or anything like that, please expect some delays with network storage. In a later video, we'll talk a little bit about storage area networks. But before we get there, let's talk about relational database management systems, or databases in general. So modern databases are referred to as relational database management systems. The reason for this is because it's a database, so it's got a structured data storage format. And the database itself is considered relational. Now, the way this will work is to store the data, we'll put it in tables, which you can imagine to be sort of like an Excel spreadsheet. And in the tables, you'll have records and fields. You can consider the records to be like the row of a spreadsheet and the field to be like the column, where every field describes a data type: first name, surname, email address, phone number, stuff like that. And every record or row is an individual entity's data record. Cool. Now, the relational aspect comes in via the tables being linked by a unique field. So, for instance, if I have a customer database, I'd probably give that customer an ID number that I use internally. And then for invoices that those customers need to pay me, I could have every invoice referencing the customer ID number, so that if I need to figure out who owes me this much money, I can go and check, okay, that invoice is unpaid. Which person owes me this money? Oh, it's Bob. Okay, what's Bob's phone number? And I can pull Bob's phone number from the customer table. Thankfully, Network Plus does not expect you to become a database admin, but does expect you to appreciate some of how databases work. And speaking of how they work, we normally access the database via a query language. Now, a query language is able to create data, modify data, and delete data. And SQL is the most popular implementation of a query language for RDBMSs. So let's talk about SQL then, or the structured query language. Now, it's a high-level programmatic language that is considered a general standard language, and then various vendors have their own unique implementations of it. Now, what this means is that, in general, SQL has some universal syntax. So once you've learned one vendor's implementation of SQL, it's a lot easier to learn another vendor's. But when you start working with more than one SQL vendor, you will notice that some SQL vendors do some things that others don't. So let's talk a bit about those vendors. In no particular order, you've got Oracle Database, normally with some version number and maybe an amendment letter afterwards. And it provides communication services to the database via TCP port 1521. Then you get Microsoft SQL Server. Please note, only Microsoft calls it SQL. Everyone else calls it SQL. And that runs through TCP port 1433. Then you get MySQL, which is an open source product, very popular for learning, that runs on TCP port 3306. And then you get PostgreSQL, sometimes just referred to as Postgre, which runs through 5432. And there are a couple more. Now, one interesting thing about SQL is because most databases use SQL of some implementation, and SQL has a lot of consistency amongst the various implementations, a lot of hackers have developed attacks and exploits that allow them to easily mess with databases. So to try and counter this, there is a movement in the database administration space called NoSQL, which is basically trying to find an alternative query language paradigm to SQL. And the idea is it's going to try and resolve a lot of the security threats and attacks by moving away from SQL. Now, NoSQL is currently just an idea. It hasn't got a specific language or paradigm just yet. So there's a variety of data formatting and organization approaches currently being used. But so far, some of the things that are standardized right now with NoSQL is that access to the database will be done through HTTPS and APIs. Now, in my opinion, this will work for a time. At some point, we will come across a great NoSQL solution, and the world will eventually move over to that. And therefore, all SQL-based attacks will suddenly be rendered obsolete. The problem, though, is whatever becomes the replacement to SQL will be widely adopted, and attackers will then have a reason to figure out how to attack it. So it'll be a matter of time before whatever replaces SQL lands up in the same situation as SQL, which is one of the reasons why I think we are still on it. I've been talking about NoSQL for a really long time, and so far nothing has properly come in and taken over from SQL. Now let's talk about something that's guaranteed to be in most organizations and businesses: emails and maybe voice communication. So first up, let's look at the email protocols. So first we have SMTP, or the Simple Mail Transfer Protocol, and it normally uses port number 25 with TCP, and it is considered our outgoing email protocol. I will diagram it just now to make it clearer. But we do have secure variations called SMTPS that will run through either port 465 if it's implicit or assumed, or 587 if it's explicitly stated that we're using TLS. Now we also have POP3. Now for some reason CompTIA is not covering POP3 Network Plus anymore, but I'm going to do it anyway because it is still used in modern networking. The Post Office Protocol version 3 runs on port number 110, and it is considered an incoming or receiving email protocol. And if you're using POP3S, the secure variant, it runs on port 995. What CompTIA does cover in Network Plus is IMAP4, or the Internet Messaging Access Protocol version 4. And it runs on TCP port number 143 and is, like POP3, an incoming or receiving email protocol. And there is an encrypted version using TLS called IMAP4S running on port 993. Now let's go and diagram what this all means. So let's have some network infrastructure where that is the sending client, that is the sending server, that is the receiving mail server, and this is the receiving mail client. SMTP, being the outgoing or sending protocol, will be used from sending client to sending server, and also from the sending server to the receiving server. Now on the receiving side of things, the receiving server will use either POP3 and or IMAP4. Now, the reason why I say and or is because a receiving server can be set up to use both POP3 and IMAP4 to deliver mail. It's up to the client which protocol it uses. Now, the reason for two delivery protocols is because POP3 is what we call synchronization based. The client and the user will not know that they've got new mail until they connect to and synchronize with their mail server. So that means if the person doesn't press refresh, send and receive, sync, or whatever the button is called, for the whole day, they will not see their new mails arriving until they do that. Whereas IMAP4 uses something called the push notification service. When the receiving server gets new mail for a particular client, the server will send a push notification to the client device telling that, hey, listen, this user has some mail. Connect, sync, and retrieve it. And then the client will connect, synchronize, and download that new mail. more or less as it arrives. So the person doesn't have to remember to press the button. And also, the client application doesn't have to have a scheduled synchronization on it, because that was the only way POP3 could actually check for mail without the person manually checking, is by having a schedule where it checks on its own automatically. But a lot of those checks will end up resulting in no new mail, which will be a waste of time and data on the network. So IMAP4 is the more efficient and better option. But like I said, both still exist. POP3 is still kept around because of its reliability and greater knowledge when it comes to problems and issues, compared to IMAP4 being relatively newer. Now as for emails, what about voice over IP or VoIP? Well, voice over IP or VoIP is where we send a telephony service, or a telephone service basically, over a data network. Now, we can also support video too as well for video conferencing. But generally what ends up happening is we'll stick to voice initially and then grow into doing video conferencing as well. Now, the client will use one of two things to actually make voice over IP calls. The user will either have a hardware phone on their desk, looks like an ordinary telephone, but obviously it's communicating via a network cable instead of a telephone cable, and we're using voice over IP instead of analog conversions. Or they are using a software phone on their laptop, their desktop, or their smartphone. Now, we do need a PBX, or private branch exchange, for telephony services to work. Now, traditional PBXs are meant for ordinary telephone lines, but what we want to have for voice over IP is a VoIP-enabled PBX, so that it can handle voice over IP as well as ordinary telephone calls. So that you can have an ordinary telephone call coming into the organization being converted to VoIP, or vice versa. Ideally, though, it would be great if we could have VoIP all the way through, internally and from internal to external and vice versa, because the cost of a data packet being transmitted over the internet is far less than a long-distance telephone call. Now, in terms of the protocols and services used for VoIP, let's check them out. So the first one that I want you to know about is the Session Initiation Protocol, or SIP, which runs through TCP or UDP port depending on setup, 5060 for non-encrypted communications. And if you are going to have encrypted VoIP conversations and calls, it'll run through port 5061 for encrypted communications. And what it does is it manages the call setup, in-call maintenance, and the teardown of that phone call, as well as tracking where is that user in the network, so it makes sure that the right phone rings, and any messaging that needs to be handled, such as caller ID and stuff like that. Now, because SIP is basically making the call happen, managing it and ending it and all of that, SIP is basically the ring-ring protocol. It is literally what makes the voice over IP phone ring. Now, it doesn't, however, carry the actual voice messages. That is handled by the real-time protocol, or RTP, which is a UDP-based transport protocol for the audio files and video if you're doing video conferencing through VoIP. And what it does is it doesn't have a specific UDP port number. It'll use evenly numbered UDP port numbers for every single segment or packet being transmitted through the network. So it'll start at 0, then go to 2, 4, 6, 8, you get the idea. And this runs within the SIP session. But then we also have a counterpart to RTP called the Real-Time Transport Control Protocol, or RTCP. And what it does is it's an out-of-band stat for the data transport. Essentially, it's not part of the actual phone call, so it's not running in RTP, it's running next to it. Both of which are happening in the SIP though. And its job is to provide feedback for things like the delivery of the actual RTP messages, tracking loss and jitter. Now, just a quick explanation of what jitter is. Latency is the delay in transmission. Jitter is how much latency varies by. So I might have a 4 millisecond latency on the first transmission and then a 6 millisecond latency on the second. So that difference is 2 milliseconds. That's my jitter. And it's basically just feedback so that we know how good is the call, so that rather than trying to maintain a bad call, voice over IP would rather just drop it and have the person try again. Hopefully the network conditions are better when they try again. And the way it does it is it uses the odd port number that comes after the even number that RTP used. So if the data message that carries the audio of the voice call was port number 6, the corresponding UDP port number that would track how did that port number 6 message work would be port number 7. So I send number 6 and I get feedback on that transmission via number 7. I send 8, I get feedback via 9. And as I said, this also runs within the subsession, but RTP and RTCP are separate protocols within that subsession. Now, if you want to get into voice over IP in greater detail, I would suggest you look into a network vendor's voice over IP specific course. Although some vendors are dropping voice over IP specific courses and building them into a video conferencing course. Nonetheless, though, you'd want to look into a more specialized networking course to get fully involved with voice over IP infrastructure and setup. Most of the stuff in this module was just to make you aware of some of the nuances of it. You are not expected to be a web admin or database admin in addition to a network specialist, but you do need to be aware of it to an extent. And that depth that we went to is the extent you need to know about it for the Network Plus exam. As always, I'd like to say thank you for watching. I really do appreciate it. And if you have any friends, family members, colleagues, peers, etc. who would want to also study Network Plus, don't be afraid to share this video with them. Otherwise though, I will catch you in the next video.